Hi. So I'm going to talk to you guys today a little bit about finding the determinant of a 3 by 3 matrix. Now, what people are traditionally taught is you take the first two columns of a 3 by 3 matrix. So I shouldn't say first two, but first and second column of a 3 by 3 matrix and put it beside the third column, and then you can have a system of diagonals starting from the first point going down into the right that you add up. The three diagonals there, you take the products, add them up, and then from the third point, third number in the top row, you take diagonals down and to the left, and you add the products of those up and subtract them from the products of the ones you just added. And that gives you the correct number, and it's awesome that it does. But in a lot of matrices, I find that this is adding work that doesn't need to be done. And we can resolve this by just really understanding what a determinant is and how it works and how cofactors come into play. So let's just hop right into this. There's a lot to talk about here. So the determinant of a 2 by 2 matrix, I'm going to use A, B, C, and D, keeping letters to keep it general, or using letters to keep it general, is the product of A and D less the product of B and C. This is the basis of your determinants right here. This is what we need to know. This is what's important. This is what everything boils down to. If you don't know the determinant of a 2 by 2, you're not going to be able to get a 3 by 3 or 4 by 4 or anything larger. So, and determinants, I'm talking about square matrices, of course, and that's just another thing that you got to keep in mind. To get a determinant, you need a square matrix, or at least, as far as I know, that's the only ones I've ever seen it done with. Now, for a 3 by 3, let's just formally show you that rule I was talking about that I don't really like. So just give me a second here. I'll write out everything in letters again to keep it nice and general. G, H, so the letters A through I, there's 9 letters there for this 3 by 3 matrix. For that rule, you write out the first two columns, A, D, G, B, E, H, right there. And so you will take the product of this diagonal, the product of this diagonal, the product of this diagonal, add them together, and then subtract the product of this diagonal, subtract the product of this diagonal, subtract the product of this diagonal, and that leaves you with A, E, I. If you're following along, I'll write this out just so you can double check me, or if you're trying to learn this, it's a useful tool to follow along and write it out. Plus B, F, G, just make sure you didn't make any mistakes, or I'll try to make sure I don't make any mistakes, but I've rehearsed this. Plus C, D, H, subtract C, E, G, subtract A, F, H, subtract B, D, I. Now, what we can do here is we can factor this out a little bit further. What I'm going to do is I'm going to take out A's, B's, and C's, and I know already where I'm going with this, so I know that wherever I see a B, I don't see A or C. Wherever I see a C, I don't see A or B. And wherever I see an A, I don't see B or C. So I can do that factorization. So A is going to be EI subtract FH. And something useful to do when you do stuff like this too, cross off the terms from what you're coming from, if it helps you keep track. So B is going to be multiplied by FG subtract DI plus C times DH subtract EG. And that kind of just helps me make sure I've got everything. That's a reason I do that, especially when your algebra gets really big, like when you're doing differential equations that are really long. Sometimes you'll have a lot of terms, and you kind of need to keep track of them. So that's just a little side note. Sorry, I'm talking a little bit quiet. Make sure to keep my voice nice and loud for you. Now, you'll notice here, this is very similar to our 2 by 2 determinants, these terms that are the A, B, and C are being multiplied. In fact, they are 2 by 2 determinants. It's the product of two numbers less the product of two other numbers. So A here, this would be the determinant of EI, if we just sort of reverse engineer it, like that. And it will notice, oh hey, that's this section of this matrix right here. And that it's called a cofactor. That's what we call it. It's the determinant of the numbers that aren't in the row or column of the number you're looking for the cofactor of. That was a bad way of defining it. So what a cofactor is when you have the determinant of the numbers that are left over from a matrix, when you eliminate the row and column that that number is in, that's what a cofactor is. Now, you'll notice with C that works nicely as well, but with B, there's been a little bit of an adjustment. What's happened here is it's been multiplied by -1. Now, when we find determinants, we need to multiply every other cofactor by -1. And the way we can sort of visualize that in our heads is if you visualize just like an infinite matrix, but it starts at a finite point, number like your first row and first column, and it's positive, and then it alternates negative, positive, up and down rows and columns from there on out. You will never get it wrong. There's a formal definition of this, but I don't want to write it out because I'm lazy. And this is enough for you to understand, really. This is all I ever needed was this picture of these positives and negatives alternating. What it really is you take -1 to the power of I plus j, where I is the row and j is the column, or the other way around, something like that. So -1 to the power of 2 for the first one is positive. This will be 1 plus 2, so it's 3, so it's negative. But you don't need to know that. You just need to know this picture. So this B lands on one of those negative spots. So the determinant for B has been multiplied by -1, and that's why it works out this way. Because if you look at B up here, the actual cofactor for B would be DI FG. It would be the other way around. It would be equal to DI minus FG. But if we multiply that by -1, what we get is -DI plus FG. Carrying the -1 through, right, which works out to be FG minus DI. And that's why this device works, is it sorts that out for you, so you don't even have to think about this. But when you go on to larger matrices, there's no device. So you should really understand how to get a 3x3 so you can move on to getting 4x4s and larger ones. Because once you get a 3x3, you can get any matrix of any size, or any square matrix of any size, I should say. So let's hop into an example. I think that's probably the best way for me to show you what I wanted to show you and why I don't like this device, and you'll see why. You might be able to see why already. You see I've used A, B, and C here, but up here A came up twice, every single letter came up twice. E came up twice, I came up twice. I could have done my factoring differently. In fact, it works out that if you stay consistent where you go along one row or one column when you're factoring out from this, that you will, it will always work out nicely for you. That you'll get the associated cofactors multiplied by the entries in that row or that column. So keeping that in mind, just think about mathematically now, intuitively, what should we be looking for? If we're looking for something that's going to be multiplied by a lot of numbers, well, let's look for where zeros might show up in a matrix. So I'm going to write out this matrix here, and I'm going to do it using this device, get the determinant using this device, just because I want to show you why I don't like this device. I'm at 9 minutes, so I'm going to have to fly, but that would be 3 times 1 times 7 plus 2 times 2 times 6 plus 4 times 0 times 8, subtract 4 times 1 times 6, subtract 3 times 2 times 8, subtract 2 times 0 times 7. Now, if we work all of that out, what do we get? It works out to be -27. I'll tell you that right now, just for, I'm short on time here. I want to show you how to actually do this properly. Now, as opposed to going through all that work there, I could have expanded this along this column or this row. And I'm going to choose the column. Keep in mind the positives and negatives. There's a reason I'm choosing the column other than that, though. If you're smart, you probably already see it, and congratulations. So 3 is the first entry. It gets multiplied by +1. 0 gets multiplied by -1. 6 gets multiplied by +1. Great, I don't need to worry about anything. If I line along the row, negative, positive, negative. The cofactor of 2, if I was to expand the matrix that way, would need to be multiplied by -1. Keep that in mind. But because I'm going to go along the column, it'll be 3 times 1 times 7, subtract 2 times 8. Now the 0 we don't even need to worry about because anything times 0 is 0. Plus 6, 2 times 2, so its cofactor, it's right there. Minus 4 times 1. That's the other thing with the column. You can see its cofactors are nice and easy. It's a little bit, when you're in the middle, it can be kind of dicey, especially having done a lot of it. So now you'll notice with the 6, this is what I was talking about by going along the column if you're really smart. But I caught this. 2 times 2 is 4, minus 4, that's 0. We don't even need to worry about that. This boils down to 3 times 7 minus 16, which is equal to 3 times -9, which is equal to -27. And that right there is how you save yourself a lot of time when solving determinants of 3x3s. Now, if you have a scientific calculator, it can do the determinant of a 3x3 or 4x4. But if in a pinch, if you need to know how to do this, if you're on a test or something, like I know my linear algebra classes, when I first had it, I wasn't allowed to use my calculator when this was introduced to me. And, as I went further on in university, I could. But you should know how to do this, and it helps you understand things like resultants when you're getting into 3D statics and stuff like that, when you need to use determinants of 3x3s or in dynamics and stuff like that. It's really useful in physics. I know those applications, and there's a lot of other uses in mathematics for these. So I hope this was very helpful for you, and thank you very much.